Okay, our second video on charging is going to focus on charging by induction. Induction is different from conduction. Conduction was two objects that are touching, that actually touch together, and electrons will flow. Because electrons repel each other, they will flow from more negative areas to less negative areas because they want to spread out, they want to get away from other negative charges. Charging by induction does not involve contact between objects, between two charged objects at least. Instead, what happens is a charged object is brought near another object, usually a neutral one, causing polarization, which we reviewed in the first video. That just means the separating of charges within an object, so one side is positive, one side is negative. And then at this point, a couple different things can happen. Let me show you a simulation of this first. We have two neutral objects, right? We know that introducing a balloon will cause polarization. Both of these objects now have negative left sides and positive right sides. I'm going to put these two objects together. I'm going to touch them together. So let's say that they started off, actually, here, let's remove the balloon first. Let's start these objects off touching. Okay, that's just a little error in the simulation. You can already see some effects of that. Polarization is going to increase the amount of, introducing the balloon increases the amount of polarization. You can see that the left-hand side is really negative, the right-hand side is very positive. What happens if I separate these objects? Like that. Now, all the negatives are stuck over here. All the lack of negatives, so positive charge, is stuck over here. And unless those two objects touch again, there's no way to write this. I could even take the balloon away, and those charges are kind of stuck. Now remember, we started with two neutral objects. Now what we have is one negative and one positive object. That is one example of charging by induction. Let's write down an example of this. So, if there's more than one object being polarized, the second object can be moved away and both objects will be charged. So let's do this. Let's say we have two objects that start off touching. They are neutral conductors. Neutral conductors. How do we know that they're neutral? We're going to draw equal amounts of positive and negative charges. 4 plus signs for positive charges for protons, 4 minus signs for negative charges for electrons. We are now going to bring in a charged object. Nothing fancy, just a charged object. There's just a little stick or something here. And let's make the charged object positive. What is this going to cause to happen? Well, the positively charged object is going to come near these two originally neutral conductors. The positive charges in here are going to attract the negative charges in our two objects. And since they're conductors and since they're touching each other, that means the negatives can move. The negatives are all going to move over to be closer, or not all of them probably, but some of them are going to move over to be closer to the positive conductor. So we've polarized our two neutral conductors. The left-hand side is now negative, the right-hand side is now positive. If we then, and it has to be in this order, separate the conductors and remove that charged object, look what happens. The positive charges, the protons, did not go anywhere, but now the negative charges are stuck here. There's no more negatives over here. They all moved over. And again, in real life, they wouldn't all move over, but a good number of them would. This now, these were originally neutral. This now has a charge of negative 2e. This now has a charge of positive 2e. We started with two neutral objects. Charging by induction, by making sure they were touching and bringing in another charged object. Now we see that they have two new charged objects. We have created two charged objects. That's one method of polarization. The second method of polarization involves a phenomenon called grounding. Oh, and notice that we never touched this object to these, okay? We never touched, that's why it's not conduction, it's simply induction. If there's only one object it can be grounded by coming into contact with an object that allows electrons to flow from the Earth, which is called the ground, into the object or vice versa. Let me demonstrate what grounding does. Grounding just means make a connection to the Earth. Earth is a really big repository of charge. Okay, Earth is electrically neutral, but if a few electrons go from the Earth into some other object, it's not going to make a huge difference. Okay, the Earth is so big, there's so many charges, and so many charges are being exchanged between the Earth and other objects all the time that it doesn't really matter. It's not going to miss a few electrons. If you have a negative object and you touch a grounding wire or some object that is connected to the Earth to it, watch what happens to the electrons. They will flow away from the negative object because they want to get away from each other. Remember, negative charges will repel each other. They try and get away from each other. They are in a very negative environment right there. Now, lots of negative charge. They see the Earth, which is more or less neutral, and they say, hey, let's go over there. That's grounding. On the other hand, if we have a positive object, then there's a lack of electrons. Electrons from the ground will see that. They don't really see things, obviously, but they will sense that, and they will move towards it. So if I touch a grounding wire to a positively charged object, it will bring electrons to that object. Okay? So that's grounding in a nutshell. Grounding is another method that can help us to charge an object. And it can do it like this. We're going to start once again with a neutral conductor. Again, we know it's neutral because equal numbers of positive and negative charges. And you'll notice that I always keep the same number of positive and negative charges. I guess I introduced this new positively charged object, but there were 4 positives to begin with in the neutral conductors. There are 4 positives to end with. There were 4 negatives to begin with, 4 negatives to end with. You shouldn't just be introducing charge or drawing as many pluses or minuses as you want all over your paper. I will be rather strict about this, okay? If we're going to use the law of conservation of charge that we talked about in the last video, you can't just randomly create new positive or new negative charges. If you start a problem with a certain amount of charge, you should end the problem with that certain amount of charge unless you can justify where that charge has gone. It will take you a little getting used to, but I will be pretty strict with that. Okay, so we have a neutral conductor, and just like last time, we're going to bring in a charged object. Let's bring in a negative object this time. This causes polarization. I should write polarization up here as well, because that's why, we always start with polarization when we're talking about charging by induction. Okay? If it's polarized, the positives aren't going to go anywhere. Remember, they're locked in. But the negatives, they are going to be repelled. The negatives in the neutral conductor are going to be repelled by the negatives in this object. They're going to go as far away from it as possible. Left-hand side is now positive. Right-hand side is now negative. Now what we are going to do is we are going to ground this conductor. We're not going to send it to its room with no dinner. We're going to electrically connect it to the ground. The charged object isn't going to go anywhere. Our neutral conductor isn't really going to change. But what is going to happen? Remember, those electrons over here tried to get as far away as possible from the charged object. If you connect this to the ground, and here's the symbol for ground, by the way, it's kind of imagine like a cord or a line or a wire going off the object, and then this funky looking arrow that points to the ground. That's a symbol electrically for ground. What we're doing is we're providing an escape hatch for these electrons. They've already got as far away from the charged object as possible, but now we're giving them a method to get off of this object entirely. They're going to sense the ground, the connection to the Earth, which is a neutral object, and to them, there's too many negatives up here. So they're going to say, hey, let's get away from these other negative charges. They're getting repelled from them. Let's go towards the ground. They're going to leave. Now, the order that you do this in matters a ton. What you now do is you're going to cut off the ground, then remove the charged object. It has to be done in that order. You have to cut off the ground first to make sure the electrons can't get back in, then you remove this. And what you're left with, sorry about my drawing, we're going a little off to the side here. Let's see. Let's get a little bit more space for us here. Okay. What you're going to end up with is an object that has been charged. Again, since those electrons left, there are no more electrons here. And again, not all the electrons left, but in this case, I just drew them all leaving. We now have a positively charged object with a charge, this time, of positive 4e. We could have the reverse happen. We could have brought in a positively charged object. What that would have done was attracted the electrons towards it. We could have grounded the conductor. Basically, what would have happened then is the electrons in the ground would have seen, hey, there's a lot of positive charges up here. Let's go towards that because negative charges are attracted to positive charges. They would have flowed up the grounding wire and into this object, and we would have ended up with an object that's more negative than usual. An object with a negative charge, I should say. So again, we see that another method for induction does not involve touching the charged object to the conductor. What we do instead is we connect the conductor to the ground, and we allow electrons to either flow from the ground to the object, or to the conductor, or from the conductor down to the ground. So, those are the 4 different methods of charging an object, of giving an object a net charge. Charging by friction, very simple, rub objects together. However many electrons are lost by one object must be gained by the other object. Object gains electrons, it becomes negative. If it loses electrons, it becomes positive. Charging by conduction is kind of like friction, but it's just touching of objects, not rubbing. And again, electrons flow from more negative to less negative. Electrons want to get away from other negative charges, from other electrons. They will tend to spread out. If there are more electrons in one object than the next, they will flow from where there's more electrons to where there's less electrons. And then finally, induction, which involves polarization as a first step, but then involves either separating the object, cutting an object in half, or splitting it up once it's been polarized so that the positive side and the negative side are now distinct and the electrons can't get back and forth between them, or grounding an object and allowing some electrons to flow up into the conductor or down away from the conductor, and then removing the ground. You now have a positively charged, or you now have a charged object. All of these different types of charging methods can be seen with the use and can be demonstrated with the use of a special tool called an electroscope. An electroscope is a device used for figuring out if an object is charged or not. I'm not sure we're going to be able to do this in class. I can at the very least demonstrate it for you, but before I do that, I'm going to show you this simulation. This is more or less what an electroscope looks like. An electroscope, it has a metal knob on top and then kind of an isolated glass chamber down here. And you can see that we have negatives and positives all throughout here. Now, I have a negatively charged object. Watch what happens if I bring it near the electroscope. It's repelling some of those electrons in the top knob down into the bottom of the electroscope. And there's a set of leaves down here, metallic leaves. As more electrons get repelled down into the leaves, those two leaves start to spread apart because now some electrons are on the left-hand leaf, some electrons are on the right-hand leaf, and they're trying to spread apart. So we can identify if something is charged by if the leaves are spread or not. If there's a charged object nearby, the electroscope's leaves will spread like this. And notice, all we're doing, we're not ever touching the object to the electroscope. We're simply polarizing it. We're causing it to have, right now, it's neutral. All the charges are distributed pretty equally. As I do this, as I bring the object near it, we are polarizing it. The knob is now positive. The leaves are now negative. And notice that the leaves are both negative. That's why they're repelling. It works the exact same way if I have a positive object that's being brought near it, except now instead of electrons fleeing the knob, they're getting drawn up into the knob. But that still makes the leaves spread apart because now they have net positive charges on them. More negatives at the top, more positives down here. But since there's two different leaves, both of them are positive, they will repel each other. So electroscopes, the leaves will spread if there's a charged object about. Now, where it can get a little tricky is what happens if we touch it. Okay, so this is just polarization. And by the way, so I said that each one of these methods can be used for charging. What does it mean when this object, how did this object get a positive or negative charge in the first place? Well, it got that charge probably due to charging due to friction. Now watch what happens if I bring let's do negative. Watch what happens if I have it polarized and then I bring the finger over and I touch the electroscope. What I've done, and I'll reset it for you. Oh, I don't know if I'll be able to reset it. Yeah, let's do that. Okay, so what I've done here, I've polarized it, I bring this over, and it's almost like I'm grounding it, okay? Because the finger is connected to a person who presumably is standing on the ground. So I ground the electroscope. Look at those electrons. They flee. The reason they flee is because they don't want to be near this negatively charged object. Negatively charged objects will repel each other. So some of those electrons, not all, are going to go into the finger. Okay? What I've done, if you count up the number of charges, is I've just left this electroscope with a positive charge for right now. If I take my negative charge away, those negatives will come back. Okay? But watch what happens if I remove the finger. Okay? Now it's not there. Those electrons can't get back. Now, if the electroscope stays out like this, that indicates that right now there is a charge on it. And you can tell that there's a positive charge because not every proton, not every positive charge is matched up with an electron. If it's charged like this, notice that if the leaves are spread out when there's no charged object near it, that means the electroscope has a certain charge. Watch what happens if I bring the negatives near it. Okay? If the electroscope has a charge, it's almost like everything is reversed. I bring in the same charge towards it, the leaves shut. What if I bring the opposite charge towards it? Look at that. The leaves have spread out even more. Okay? So if an electroscope has a net charge on it, it's kind of reversed. If it didn't have a net charge on it, okay, so right now the electroscope does not have a net charge on it. I bring a charged object near it. The leaves separate when the charged object is near because it's polarized. They go back together when the object leaves. However, if I have an object that is charged, now this electroscope has a negative charge to it, the electroscope will be, the leaves will be separate, okay? If it is charged and there's no other charged object near it, then the leaves will separate because there's too much charge of one type. That extra buildup of charge happens in the leaves, and they'll spread apart because the leaves will repel each other. If I bring a charged object near it of a different charge, so the electroscope is negative, if I bring a positive charge near it, the electrons in the leaves get sucked up towards the knob, and because they want to be near the positive charge, the leaves go together. If I bring the same type of charge into the picture that the electroscope has, we're going to separate the leaves even more. So again, quick summary. A neutral electroscope, the leaves will spread apart if either type of charged object comes near it. Oh, do I have? Okay, there we go. So a neutral electroscope, no matter what type of charge comes near it, the leaves will separate. If the electroscope is charged, by the way, this is the way we have to charge it, charging by conduction, then so let's see, this object is the electroscope is positively charged now, there's more protons than electrons, and you can see that by counting. Since it's positively charged, if I bring the opposite type of charge over, the leaves close. If I bring the same type of charge over, the leaves widen even more, because now there's a huge amount of positive charge on the leaves because there's basically no electrons left down here. This is all a little tricky. I don't blame you if you think this is tricky to understand. This and the other types of charging are probably the second hardest part of this unit. What I want you to think of when you're thinking of charging, and you have these assignments where you have to talk and discuss and describe and show and depict different types of charging, you should always be thinking in your head, it's a cause and effect. Something happens, how are the electrons going to respond to it? Electrons are very simple. They're attracted to other negative charges. They are repelled by other negative charges. They are attracted to positive charges. Repelled by negatives, attracted to positives. If you keep that in your head and there's some cause and effect that happens, all you have to think of is what are the electrons going to do as an effect of this cause? Okay? Something changes. How is that going to affect the electrons? Are they going to be repelled away? Are they going to be attracted towards something? That's what you need to be thinking of. Okay? Again, we'll do some more electroscope stuff in class, hopefully. You'll get a little bit more of an idea of how to work with charged particles, how to work with different types of charging. Since this, like I said, this is a tricky topic. It's hands-on, but it's tough to do. It's tough to do a good job with it sometimes hands-on. We will talk about this more in class. If you have any questions, please don't hesitate to ask. And I hope that you have a nice day. So we're pretty much done here. If you have any questions, let me know. I'll talk to you later.